Hi everyone, just a quick podcast on last week's workshop. We were back to the old ready moors business again, and the first thing I suggested that you do is look at the correlation between the different things. Resume slideshow, don't know what happened there. This panel here shows you the relationship between the placement and no placement students, and there doesn't appear to be one. So the scores in the for the placement students are not dependent on the scores for the no placement students, which is good, because in all our sort of comparisons using things like the t-tests and what have you, then the one of the things quite important is that there isn't a relationship between them, that they're independent samples. You can use varieties of t-tests and so on which are for dependent samples, okay, but straightforward one is where we've got independence between the samples. That's demonstrated by this lack of correlation between the two variables. Right? When we start with doing our Mann-Whitney tests, it produces a highly significant result here. This is the test statistic calculated from the Wilcoxon test, has this value, W, and this is the chances of getting this value if there's nothing going on, okay, if the null hypothesis is true. And you can see that the value is extremely small. It's close to 0. This value in the box here, e to the minus 12, is this one. Okay, so it's got 12 zeros. It doesn't look like there's 12 there. Maybe I've not done enough, but loads and loads of zeros and then 2. Right, so the basic idea is that with all stats, it proceeds from the notion that all the samples are coming from the same population. There's no difference between the samples, and that's what's called the null hypothesis. Okay, you calculate we're at statistic of interest. In this case, we're calculating the Wilcoxon test statistic, and different values can come up, but some of them are more likely than others. The likelihood of getting a t statistic as large as this under the null hypothesis is extremely small, 1 chance in a trillion. Okay, so that's not likely to happen. So what we say is that we don't want to accept the null hypothesis that the samples come from the same population. We think maybe they come from different populations. But the trouble with the Wilcoxon, no, not the trouble. The thing about the Wilcoxon test is that although it'll cope with samples from populations that are not normal, okay, it's a non-parametric test, it requires that the samples come from populations whose have the same shaped distribution, even if it's not a normal distribution shape. Okay, but if there's a difference in location as well, we can't disambiguate those two things. Now the Kolmogorov-Smirnov test is something for comparing the shapes of the distributions of samples. Okay, and the hypothesis here is again that the two samples originate from the same distribution, same way as all statistics works. Okay, and it calculates its thing, its Kolmogorov-Smirnov test statistic, and in this case we see again it's got a very small value, 10 to the minus 10. So we can reject the idea that the two samples come from the same population, but we don't know if the difference is due to the shapes of the distributions or the shapes and the means as well. Okay, so what we've got to do is remove the difference in the means using our data transformation, which is simply subtracting the difference in the means from all the values in one of the samples, so that the two samples then have got the same mean. Okay, so if we then find a difference and we do this test, we know it can't be because of the means, because we've taken the mean out. And in fact, when we do that, we find that the test statistic is of a value, a number that happens quite frequently, because it has a p-value that is relatively large, in fact bigger than 0.05, so it happens more frequently than 5 times in 100. So we'd say that that's good evidence that the shapes of the two distributions, although the means are quite different, okay, which is what we're trying to find out, the shapes of the two distributions are similar. And if you can remember, our histograms and so on seem to indicate that as well, didn't they? So in that case, it's valid for us to use the Wilcoxon test to compare the means. So we can then go back to our test statistic and say that our Martin-Whitney-Wilcoxon test did give us a significant result, because we know now that the two samples come from distributions with similar shapes. For the peer reviewing, I've written a document this week, because it's quite long to go into all this, so you can read about that inside. I think it says workshop 5 there. It's probably inside this week's workshop, but you'll find it, I'm sure. Bye.